The last section in chapter 2 talks about the concept of continuity. And I wanted to go over and talk with you guys a little bit about what continuity is and kind of get the idea that it's something that you most likely already know. So the idea of continuity is really just the idea of where a function exists. Okay, so in other words, if we have the limit as x approaches a from the right of f of x, if that equals f at a, then it means that it's continuous from the right. And of course, under the same idea, if if the limit as x approaches a from the left of f of x equals f at a, then it is continuous from the left. All right? So the idea of continuity basically means that it's in the domain from that direction. Okay, so a lot of times when we talk about continuity, we're really talking about the domain. Right? And just to give you an idea of the idea of a discontinuity, a discontinuity is a location where a function does not exist. Okay, or you might have to lift up your pen if you're tracing the graph of it. So function is non-existent. All right, and let me give you just a really basic example of some of the different types of discontinuities that exist. Right. So for instance, we might have a really basic function. F of x is equal to maybe something like x over x cubed minus x. Right? And we know that we can simplify that, and we know right away that x cannot be equal to 0 or 1. Right? But if we simplify this by factoring out an x from the denominator, and so we can see actually that x cannot be equal to plus or minus 1, but it can't be equal to 0 either. All right, so so what's the issue with this? Well, there's actually two types of discontinuities going on here. All right, and we can certainly look at the graph of this function if we wanted to, but the discontinuity types, if you can cancel out the x's, so since the x's cancel, x equals 0 is something called a removable discontinuity. All right. And the other type, x equals plus or minus 1, right? Those are asymptotic discontinuities. So asymptote discontinuity. I think my math lab calls them an infinite discontinuity. All right. Just because it does approach that value of infinity or negative infinity. There actually is one other type of discontinuity, all right, sometimes called a step or a jump discontinuity, and that doesn't really happen that often in mathematics. So just to give you an idea of what that looks like, let me get rid of some of this stuff just so I can draw a picture of it. But for any of you that have ever seen the function f of x equals like a ceiling function, all right, or a greatest integer function, that's a step discontinuity, all right? And basically what a step is, it just says round up to the nearest integer, okay? So round up to nearest integer. So for instance, let's say we had f at 2.999, that would be the ceiling or the greatest integer of 2.999, which would be equal to 3. And so what does that function look like? Well, it looks like this. If you plug in 0, so let's say this is 1 and 2, and so at 0 there's a solid dot, and it kind of just follows this path until you get to 1, there's an open circle. and then it goes up to the next integer, which is 1. It follows that until you get to the next integer, and then it does the same thing over and over and over again. All right, and so notice there's a discontinuity here and here. All right, those are called jump discontinuities. Okay, sometimes called step discontinuities. Again, we don't worry about those too much in this course. So these are jump and step discontinuity. All right, so this is the third type. And the other two types, remember, are the removable. And then finally, there's an infinite discontinuity, or sometimes the asymptote discontinuity. All right. So just to give you a few examples of how continuity works and what the types of questions you're going to be looking at. Let's say we have this graph. So this is our function f of x. And the question is, where is f continuous? All right, so that's the question we're asking. And so again, what you usually do is you just trace the graph until you have to lift up the pen. All right, so from right here, now we know that the function starts at 1. All right, so it's certainly continuous starting at 1, and it's inclusive of 1 because of the solid dot. And I'm going to trace this function, and I notice that I'm just going to keep tracing it until I get to 2. Now, once I get to 2, it's not continuous at that point. It's not in the domain. And then it just keeps coming back down until we get to 3, and notice that there's an open circle at 3. All right, so from 2 to 3, it's continuous. And then we have that jump. So we start up again at 3. And then from 3 to 4, and by the way, this is an asymptote discontinuity. From here to here, all right, so from 3 to 4, there's another discontinuity, all right, and this one is going to be a removable discontinuity at 4, all right, so we go from 3 to 4, all right, and then finally, we don't have to lift up the pen at all. It just kind of goes there, and then it goes down to 6, all right, so but notice that the function is not defined at 4. All right, so we still have to keep it undefined there. So it's not in the domain, or it's not continuous there. So this would be from 4 to 6, inclusive of 6. All right, so that's what we mean by continuity. All right, basically you can draw the picture or you can draw the graph without lifting up the pen to be able to jump over a hole or to get rid of an asymptote discontinuity. All right, so in the rest of these types of problems, we're going to be taking a look at analytic ways to be able to look at continuity.